Hello. So go ahead and try use this as your first lecture. We'll see how it goes. Um, again, at 10 o'clock, I'll open up a Zoom chat for you all to ask questions if you have them. So take advantage of that opportunity if you need to. And this lecture will be a part of that. But yeah, so we'll get started here. Share my screen with you and we'll go through it. Okay. So we're moving on to section 2 of chapter 8. So if you don't remember section 1, remember we're dealing with exponential functions. So it's y equals a times b to the x power, where b is our growth factor or decay factor. So growth or decay. So when b is bigger than 1, you have growth. And when b is between 0 and 1, you have decay. And our graphs look like that for growth. And it looks like this for decay. So today we're going to throw in some transformations, some things that are going to change the way this graph looks. Some of it we've already actually seen a little bit of it, but let's see what else we have. So the transformations of exponential functions that we have are a stretch, a shrink, a reflection, or a translation. There's two types of translations. We're really going to only worry about one for our class. So you have a stretch. So again, we have y, erases, y equals a times b to the x. And then now we're going to add in a plus k. So we've seen plus k before. So you may already know what it's going to do. We'll talk about what that does here in a second. But y times b to the x plus k. So you have a stretch. So basically that means it's going to move faster when a, or the absolute value of a, is bigger than 1. So it's going to become exponentially faster than if it were just y equals a times b to the x, where a was 1. You have a shrink when the absolute value of a is between 0 and 1. So again, we're talking about a, we're not talking about b. We're talking about the number in front of it. So for example, y equals 2 times 2 to the x. That would be a stretch. Or y equals 1/2 times 2 to the x. That would be a shrink. Both growth, because 2 is bigger than 1 for b, but this one will be going up quicker. It looks something like this, where this would be going up slower. So that's what a stretch and a shrink do. Okay, reflection. You have a reflection when a is negative. So for example, if we have y equals -2 to the 2x, that reflection happens over the x-axis. So before, our graph was like this in red. But then the reflection in purple, it looks like this. So it just reflects over the x-axis. Then in translation, this is where k comes into play. So if it's plus k, everything moves up. If it's minus k, everything moves down. And then going back to that weird word that we saw before we took a little bit of a math hiatus, word asymptote. Asymptote, remember that's where the line can't cross. Our exponential graph goes right up to the asymptote but doesn't cross it. The asymptote is y equal to k. So before, this is the type of problem we saw, y equals 2 times 2 to the x. Well, k is technically, I'll change colors for that, 0. Well, then our asymptote had been up to this point, y equals 0. But if we had y equals 2 times 2 to the x plus 2, we take that same graph and it moves up 2 and now has an asymptote at y equal to 2. So the two big things really worry about there, you'll see the stretch and shrink when you plug it into your x and y table, but the reflection and translation, that's the new part. That is the new part here. So state the transformation. So 5, so A is equal to 5, which means we have a stretch. A is equal to 1/2, and A is negative. So you have a shrink and a reflection. And remember, both of those would be exponential growth. Here, B is 1/2. There's no A, so there's no stretch or shrink. There's no reflection. But we have plus 3, so it's going to move up 3. And then here, A is equal to 9. So you have a stretch. B is 3, so you have exponential growth, but then we have minus 1. So we're going to move down 1 as well. Your asymptotes, well, here y would equal 3, and y would equal negative 1. Let me write that. Negative 1. Okay, so those are all of the types of transformations that we will have. E is an irrational number, approximately 2.17. We have all these formulas you can use it for, but the compound interest formula is A is the money in your account is equal to P, which stands for principal, or the amount you start with. So P is starting amount. E is this number. It's about 2.7 or 17. And then R, the rate. So R is the interest rate. As a decimal. So don't write it as the percentage. So don't write this as 5.5. Otherwise, it's going to be a huge number. And that's not what we want. We want the number to get a little bigger. And then T. T is time. So those of you that have taken Mr. Moore and Mr. Pasota's classes, you may have seen this before. I'm not quite sure which class they talk about it in, but this is where you would see that. Suppose you invest $1,050 at an annual interest rate of 5.5% compounded continuously. So we're using this formula. How much money to the nearest dollar will you have in the account after 5 years? So our starting amount, P, that's 1,050. Suppose you invest. It means you started, we put it into the account. R is our interest rate. It's 5.5%. We want to write that as a decimal, so 0.055. And then T is time. Well, it wants to know after 5 years. So T is 5. So the only thing we don't know is A, because E is a value that you have on your calculator. I can show on a calculator in just a second. We're going to do this problem, and I'll show you on a calculator how we can do it. So A equals $1,050 times E to the 0.055 times 5 power. Then at this point, these are all values we know. We can just plug that into our calculator. And that's exactly what I'm going to do here in just a second. I'm going to write it down so I can remember what it is. And then I'm going to show you on my calculator how to do that. So I'm going to stop sharing, and you're going to watch me try to find the calculator on my screen. Let me find my calculator. I can't minimize, so I'm going to search for it. Okay. Share screen. Okay. Now you can see my calculator, I'm hoping. And maybe a little bit actually of the work that we were doing earlier. We'll see. So 1,050. I know all of you are going to have graphing calculators. And the nice thing is being at home, you can get a graphing calculator actually on your phone. I have one because of course I do. With an app called Desmos, so D-E-S-M-O-S, D-E-S-M-O-S. It's a good graphing calculator that you can have on your phone. But if you have TI at home, this is what I have. It should work pretty similar if you have another type of calculator. So down here, you see this LN button. Well, the second button to it is e to the x. So we have that e value here that we want to use. So second, ln gives me e. The little caret tells me it's taken to a power. And then I take what power it's to. 0.055 times 5. And it's all there for me. I just hit enter. Boom. And he asked me to do it to the nearest dollar, so $1,382. And I'll switch screens here so I can I'll switch back to my smart page here so that we can then write that answer down. $1,382. So when you talk about compound interest, your money after 5 years, you gained almost $300 by not doing anything, just letting the bank hold on to it and use it for whatever they need it for, and then they give you interest for that. Unfortunately, it's the same thing when you owe people money. If you owe on your car, or eventually when you have a mortgage, you're going to have not compounded interest, but different types of interest that follow a similar idea. I think depending on what it is, it will charge interest to you. So when you talk about student loans, some of you will have to be taking those out here in a little bit. Currently, I pay almost as much in interest as I do for the loan itself on my student loans. That's just the reality of how the math works, depending on the interest rate too. So just something that you know that this is something practical that you can use. You may not use compound interest for your loans, but it's definitely something you will see. So you can tell me, Mr. Adams, when are we ever going to use this to see how much money you're losing? That's when you use it. Always good stuff. So the last thing we're going to do, we're going to do 2 examples of graphs. And when we do these graphs, I want to talk about asymptotes as well. So what's the asymptote here? Well, what does k equal? Remember, that's y equals k. Well, k here is 3. So y equals 3. Fantastic. I'm going to put lines in actually. So I'll fix that. And then I want to line. Oops, actually, that's what I'll do. And then I want to line. That's me. New line. Then a line going across. Awesome. Okay, so let's do our chart, our t-chart here. So again, it's the same x values I want you to use, -2, -1, 0, 1, and 2. So what I like to do is I like to do y equals a times b to the x first, and then at the very end, any translations that we would have. So in purple, I'll do that first. So y equals, a here is 1, 1/2 to the -2. And then we'll do +3 at the end. So 1/2 to the -2 first is all we have to do. So again, that negative exponent flips the fraction and it becomes 2 squared, or 4. And then I'll do any translations I have. +3. So this is 7. So if you want to follow the pattern of b tells us the next number is, you can do that, but it has to be with what's in purple. The next number will not be half of 7. It'll be half of 4 plus 3. So what I mean by that is, let's look at that. 1/2 the negative first, or 2 to the first. Well, that's just 2. See, 4 and 2. Half of 4 is 2. But that's not the whole story. The next number is +3 of that, 5. So again, b is our decay factor here. We're going to have exponential decay, but half of 7 isn't 5. The factor happens here before we move everything up. So then it's 1/2 to the 0 power. Anything to the 0 power is 1. So 1/2 to the 0 power is 1. Add 3 to that, you get 4. Again, half of 5 isn't 4, but half of 2 is 1. So then you can kind of see where we're going from here. 1/2 to the first, well, to the first power, that's 1/2. If I add 3 to that, that's 3.5, or 7/2. 1/2 squared. 1/2 squared is 1/4. And I'll write that cleaner here for you. 1/4 plus 3. That's 3 1/4. So again, we're getting really close to our asymptote. In this case, your asymptote is 3, but it's not going to quite get there. If I kept on going, this fraction would get cut in half, be 3 1/8, 3 1/16, 3 1/32. You're never going to get to 3. It's going to keep getting closer and closer and closer without crossing. Or if we wrote that as a fraction, that is 13/4. So a weird fraction to deal with. You can leave it as 3 1/4. That's fine with me. So let's graph this now. -2, 1, 2, 3, 4, 5, 6, 7. -1, 1, 2, 3, 4, 5. 0, 4. 1, 3. No, sorry, 1, 3.5. Because our asymptote is 3. It'll never be 3 there. 3.5. There we go. 3 1/4. But again, our asymptote is 3. It's this line it's never going to cross. Because usually it's been 0 so far, but k moves everything up 3. So there's where it's not going to cross. So you have 1/2 x plus 3. Okay, here we have a, and we have a k. So that stretch basically is just going to go up quicker than if a were 1. That's all it is. Nothing that we really notice when we're graphing it ourselves, but just it's what's going to happen. I have my coordinate plane in there. Do my XY chart. Again, I want to use those same x values, -2, -1, 0, 1, and 2. But first, I want to find a times b the x. Then add k at the end of it. So for our sake, 2 times 2 to the -2nd. And then we'll do -3, which will move everything down 3 and have our asymptote be y equal to -3 in just a second. But let's go ahead and finish this first. That's 2 times 1/2. Remember, it flips the fraction squared. Or 2 times 1/4. Well, 1/4 of 2, that's 1/2. -3. Ooh. So don't let that freak you out. 1/2 minus 3. That's just -2 and a half. Let's try the same thing now with -1. When x is -1. So again, don't let the negative fractions and don't let the negative exponents and fractions freak you out. Stuff that you can handle. Now this just becomes 1/2. Because 1/2 of the first is 1/2. 2 times 1/2 is 1. -3. You get that it's -2. So again, this is what's getting doubled, 1/2 to 1. Well, then we can guess the next one before we do k will be 2. Let's see. 2 times 2 to the 0 power. Anything to the 0 power is 1. 1 times 2 is 2, but then we're going to subtract 3 from that. And you get that 2 minus 3 is -1. Got that cleaner. -1. There we go. Two times 1 to the first, or sorry, 2 to the first. That's 2 times 2, or 4. -3. That's a positive one. Two times 2 squared. That's 2 times 4. Which equals 8. -3. That is 5. So it shoots up pretty quick there. So I'm going to cheat, actually, and I'm going to move that line down. There we go. So let's graph it. -2, -2.5. With our asymptote here at -3. -1, -2. So again, I'm starting to go pretty quick. 0, -1, 1, 1, 2, 1, 2, 3, 4. Sorry, 1, 2, 3, 4, 5. So then you have your asymptote there. It'll shoot up. And there you go. So that will be your graph for y equals 2 times 2 to the x minus 3. That compound stuff, you won't have anything on your homework. But when it's time for your project for this chapter, that's the kind of stuff that you're going to have. So the nice thing is that you can always come back to 8.2, this section here, and rewatch that part if that's helpful for you. Okay, well, so that's the first section of stuff from home. Hopefully that goes well. Again, I'll be posting this. So today is March 19th. I'll post that later tonight. So hopefully you can watch it before the 10 o'clock Zoom meeting that I will have where you can ask questions over this section. I'll post the homework when I post this lecture. I'll try my best. Power School obviously isn't being our best friend today. but hopefully I'll get a chance to post that maybe when traffic's a little slower. But yeah, hopefully this has been helpful for you and you'll get a chance to learn something from this and ask questions when you need it. All right, see you next one.